Welcome to this video. We are going to learn about something called the equation of state of an ideal gas. First, let me just write down that equation. It's pressure of a gas times volume of the ideal gas is equal to the number of moles of the ideal gas times something called the ideal gas constant times the absolute or Kelvin temperature of the gas. We'll give you this value later, but for now let's just say this is the ideal gas constant. It's a number that never ever changes. Ideal gas constant. So we'll see a value of that later. We'll use the value to solve some problems. Why do we call this? Well, first of all, you've probably seen this equation, and you've probably called it the ideal gas law. Why are we giving it this fancier name, equation of state of an ideal gas? And the reason is because pressure, volume, number of moles, and temperature for a gas, those are called the state variables or the state quantities. They tell you about the state variables or state quantities. They tell you about the state of the gas, what's its pressure, what's its volume, and so forth. I want to put down the units that we will be using in these equations when we use this equation. Pressure will be in Pascal, right, which is a Newton per meter. Volume will be in meters cubed. Number of moles will be in, amount of substance, N, is number of moles. It's measured in moles. And this has to be measured in Kelvin. So what is T? It's the absolute or Kelvin temperature. The absolute or Kelvin temperature, right? So you are not allowed to ever You're not allowed to ever use the Celsius temperature, theta. You cannot use a Celsius temperature in this equation. No. In fact, here's an example of how true that is. Let's say two substances. There's two gases, ideal gases, and one is A, the other is B. They have the same number of moles in each. We could rearrange for N and say N is equal to P times V over R times T. So the pressure of A times the volume of A over R times the temperature of A is going to be equal to the same thing for B. Pressure of B times B's volume, right? And then this in the denominator. The R's you think cancel, that's true. And then you might say, look, why can't I just plug in degrees Celsius into T in both of these equations and let the units cancel out? Can't you do that? No! Even if the units cancel, you still have to be canceling out Kelvin as your unit. Still use and cancel out Kelvin. That's how rigid this rule is about using the absolute temperature. So if you see the letter T, it literally stands for the Kelvin temperature. Use Kelvin. Okay, we have some extra room here, so let's go ahead and write down the value of R, which never ever changes, is 8.31 joules per Kelvin, or Kelvin to the -1. And then you also have moles to the -1. And the units work out, believe it or not. If you plug that into the equation, you can see that the units work out. I'll leave that as an exercise for you. Okay. An ideal gas doesn't actually exist in the world. We don't have that. So real gases is what we have. Real gases are what we have in the world. How do you know whether or not a real gas will actually behave like an ideal gas? When does it approximate an ideal gas really well? And when does a real gas fail to behave like an ideal gas in the real world? So here's the answer. A real gas will act ideal if pressure is relatively low and temperature is relatively high. Right? That's the basic answer. And it won't act ideal when you have a really high pressure. And it also won't act ideal when you have a really low temperature, super cold. Okay. Why is this? Now this is a low temperature for gases relative to gases, high temperature relative to gases. Why is this? First thing, one of our assumptions about ideal gases is there are no intermolecular forces between molecules. Now, this assumption will only be true when molecules are very far apart, relatively very far apart. Okay. So here's the idea. Here's the idea. You have a molecule here, and way over here you have a molecule. And let's say they're moving off in opposite directions. When they are really, really far apart like this, they will feel almost no force of attraction. And so they will continue moving along their paths. But if they're very close to each other, then now they will feel significant attraction, and they'll stop moving where they're going, right? They won't continue on their paths, and they'll kind of bend around closer to the other one. And we don't want that, because that's not what we assume. We assume the opposite, that there's no force between the molecules. And so for that assumption to be true, we must assume that they're very far apart, just like we've written. So here's the cool thing. Let's take our ideal gas equation, the equation of state of an ideal gas. Pressure nRT. Under what circumstance, what does it mean if the molecules on average are very far apart? It means that the number of moles divided by the volume is a low value. When you compare how many moles there are, there's not that many for the volume, and so the number of moles, those moles are spaced out. They're far apart. So if you say molecules are far apart, then in effect what you're saying is that this ratio is low. There's not a lot of moles, and there's a big volume, so the moles are all spread out across the volume. Let's look again at this equation. If we divide both sides by v, then now we'll have n over v. I also want to divide both sides by r times t to get the r and t to go away. So the r and t cancel, the v cancels on the left side. And what we now have is n over volume is equal to 1 over r times p over t. So look at this. How do you get n over v to be low? When this is low, we can assume that the real gas acts ideal. A gas acts ideal, right? We can assume correctly a gas acts ideal when this is low. How do you get this ratio to be low? Make your pressure really low, or make this really high. And this explains why a real gas is ideal, acts ideal under these circumstances. So there it is again.